Okay, student. Now I will talk about motion in two dimensions, which is section 4.1, page 89. In general, we are talking about, we are dealing with vectors. If we have three bodies, in our example or in our explanation now, we have the body A, the body B, and the body C. The object A is moving along the x-axis, and the change in its position is x minus x naught, or x2 minus x1, or x final minus x initial in x direction. X direction, which is x hat, or I can use I hat, which is denoted to x direction. Also, for the object B, it is moving along the y-axis. So I can find the change in position for B is y minus y naught, or y2 minus y1, as you like to put in y direction. Okay, what if I need to find the velocity for A, the average velocity for A? It will be equal to the change in position, which is x minus x naught divided by delta t. It will be in x direction. So this will be VA just in x, and the component in y direction is 0. Also, the velocity for B as a vector, velocity for A as a vector, it is in x direction, is equal also to 0 in x direction plus y minus y naught over delta t in y direction. For A and for B bodies, the direction is poorly just for x direction or in y direction. But what if we have a different body moving in both directions? This body, C body, is changing its position according to x and to y. As we see here, the change in position for C is the change in x component and the change in y component. So we have two components. Okay, what if I need to compute the velocity for the object C? The velocity for object C, it is the change in the position. I can take it D, the change in position, divided by delta t, which is equal to delta x over delta t in x direction plus delta y over delta t in y direction, which is the same as x minus x naught over delta t, which is t minus t naught, in x direction plus y minus y naught over delta t in y direction. This is VC as a vector. This is the velocity as a vector. So the velocity for the object C has two components. This is VC in x direction plus V for the body C in y direction. This is y direction. This is VC. Also, if I need to compute the acceleration, for example, for the object C, it will be the acceleration in x direction plus the acceleration in y direction. Because the position vector and the velocity vector and the acceleration vector are vectors, then they have components in x and y, and if we need v z z hat plus a z z hat, we will not work with the third dimension, which is z direction. We will deal now with two dimensions. So we need to know now that we have for each vector, position or velocity or acceleration, we have two components. Let us see now the equations of motion. We know this is this equation, which is x is equal to x naught plus v multiplied by t plus half at squared. For the position for the object A, we have two states. The first one, if we have acceleration is 0, we have a uniform velocity. The average velocity will be equal to delta x over delta t. Velocity is equal, Vx is equal to delta x over delta t. Okay, I can find that x minus x naught, which is delta x, is equal to velocity multiplied by the time period, which is delta t in this case. And if I have acceleration, if a not equal to 0, I can use this equation, but for the x component. So because a moves just in x direction, I will use this equation for it. The change in y direction is equal to 0, because the body x or the object x doesn't change its y position. It is at y equal to 0, and the object b at stationary at x component will be for it x equal to 0. Okay, now for object b, the change will be in y direction, and this first equation, it is the first part of this long equation, but for a in y direction is equal to 0. But if the acceleration not equal to 0, I can use this long equation. In general, I have these equations of motion. I will use them in the future for, you will see that for x direction and y direction separately. They are independent of each other. The motion in x direction does not affect the motion in y direction. So I can use this equation, which is contact the velocity and the time and the position in x. This is the second equation, which gives me the velocity in x direction, v2 is equal to v1 plus a in t multiplied in t, all in x direction. This is the third equation, v2 squared is equal to v1 or v naught. You can write it v final and v initial squared plus 2a multiplied by the position, which is in x direction is x. And we have, this is the fourth and the final equation, which is x is equal to x naught plus vx multiplied by t. It is the same. We use just the equations of motion, but we use once in x direction and another time in y direction. We will see through examples when we use these and when we use these equations. If the body is moving in x component, in x direction, then we will use these equations. If the body is moving in y and changes its altitude, we will use these equations. Look at the examples, please, and thank you.